Hey everybody, it's Bob Crossan, Senior Managing Editor for Water and Waste Digest, and throughout the entire rest of this year, we've been featuring our 2020 WWD top projects. Today I have with me Jim Hagstrom, Managing Director of Technical Practices for Carollo Engineers. I have Alex Eckster. He is Technical Director at Eckster Associates. I also have James Carr and Travis Elliott from the City of Chico. James is the Wastewater Treatment Plant Manager, and Travis is the lead wastewater operator. And we're going to talk about the City of Chico automatic ammonia control using a machine learning algorithm. So yeah, thank you all for being on the call with me today, and congratulations on a top project.
Thanks for having us.
So I want to start first with some context here. James or Travis, you would probably talk to this more directly. Could you describe kind of the plant, the community that you serve, and any history of the plant that you wish to share?
Okay, start off on that. The City of Chico's plant basically is a traditional activated sludge process. It currently has a capacity of around 9 million gallons a day. We fully nitrify. The plant really became an activated sludge plant in the early 70s after the Clean Water Act. It's been expanded a few times since then, the old original plant in 1990, and the current newer facility in 97 and around 2008. We have a dry weather flow typically of around 6 million gallons a day. It's located in the northern Sacramento Valley. It's a college community with population, it serves a population of around 90,000, counting, some unincorporated areas and the city itself. We run a 8-hour work shift, which is a little non-traditional, I think, for the plant our size. We're able to, with automation, do more remote monitoring than a lot of places, and through our design and process control, that allows us to not have to staff 24 hours a day. At the time of the project, we have more positions, and we are pretty lightly staffed at the moment through difficulties of getting qualified people. We have 7 operator positions. We have 4 of those filled. During the whole process of the project that we're discussing, we only had 3 operators for most of that process as well, which made it more difficult. We have 2 electrical positions. One, it's been on and off with the second position, but the main lead electrical person is carried through the project, had a lot to do with the project we're discussing. Probably due to, what that probably summarizes a lot of the, typical processes. The plant itself, being traditional activated sludge, has standard primary treatment, and standard secondary treatment, liquid chlorination for disinfection, and we discharge to the Sacramento River.
Gotcha. Travis, is there anything you wanted to add to the context of the project on your end?
I think he summed up are you looking at for the project or just the general
the plant or the project?
The plant or the project?
Let's start with the plant, maybe.
The plant?
Yeah.
So, like James was saying, we have a very small staff. We don't have mechanics, so the operators are in charge of operations and maintenance. It's a large challenge to keep everything going, but we have a great staff, and with the staff that we we're able to implement this project and actually get it going with the help of Alex. So that's about all I have.
Bob, one of the things that I think is important is that the expansion in 2008 was performed anticipating a significant uptick in growth in terms of flows and loads to the plant. That was based on some regulations looking to eliminate septic tanks, and that was never realized. And so one of the big challenge that James and Travis had to deal with is the fact that they had a plant that at some level was over-designed because they just didn't see the flows, and that added a lot of complication to their operations staff to try to meet permit, and added some instability to some of the process equipment was there. So meeting a difficult discharge standard is tough enough, but you couple it with the fact that they had to do it with some equipment that was perhaps oversized, anticipating flow made it even a bigger challenge for them.
Yeah. So yeah, let's get to the core of this project then, because you touched on this aspect of having a little bit smaller of a staff and the challenges that can bring. So I imagine this automation thing is really, really helpful for you guys to make sure that you can continue to do the great work that you're doing. The core aspect of this project in particular was the dissolved oxygen algorithm. What kind of led you guys down the path toward doing this? Is this just an extension of the current automation that you had in place and you just felt the need to help out? What was kind of the reasoning that you guys were looking regarding that?
So in 2014, our previous supervisor had reached out to Carollo Engineers. We were having some issues with process stability and meeting our coliform requirements. And one of the things they had recommended was an automated SRT controller that was an online SRT controller that continuously calculated the SRT throughout the day. And the vendor that we went with was Alex Eckster's SRT master. And through that process, we were able to stabilize the plant, but we had mentioned to Alex that we were still having disinfection issues and these weird anomalies of problems, and we weren't sure exactly what was going on. And we was due to breakpoint chlorination, going in and out of breakpoint chlorination at certain times of the day, but it wasn't obvious, and we didn't really have instrumentation other than our lab analysts going out, physically grabbing a sample and saying, hey, there's ammonia in the effluent, there's a trace of ammonia in the effluent, and we would make adjustments to the air, and it was really challenging for the staff. And Alex had mentioned that he also had a DO master, his trademark DO master program that he had implemented in another plant, but he really wanted to look into, and we had kind of shot this off each other, looking into the using a residual ammonia to run the blower system to try and save energy, and also to actually know what we're discharging, or know that we're not bleeding through ammonia out the back of the aeration systems, and eliminating that issue with the breakpoint chlorination. And that's kind of what led us to down the road to start. So
yeah, Alex, would you like to add to these systems that he's talking about that you presented?
Yeah, so yes, sure. I would be happy to. So the plant is very unique, as you realized. It is staffed just 8 hours a day. It is there are only 3 operators at the time, so they have extreme stress on the staff, and meantime the operation of the plant had room for improvement. So the first thing we install is the SRT control system that in real-time control by controlling the slide gauge, which is another name for solids retention time, with accuracy plus minus 5%, and working with the staff over a year period, optimizing that set point for sludge gauge for each season, we were able to stabilize the process. And we have not seen since then some problems that we have seen prior to 2014. After that, it doesn't mean that there were no problems at all. There are still some problems remain. One of them was oscillation of the airflows. And from time to time, unfortunately, the staff had to come to the plant in the middle of the night and restart the blowers because they were turned off automatically to avoid the surge. And that was caused by these oscillations. In addition, there, in our opinion, was significant energy use, and we thought that there's an opportunity to reduce energy use significantly. Finally, as Travis mentioned, because of breakthrough of chlorine, of nitrite and ammonia, because the plant has a free chlorine disinfection, even a small amount of nitrite takes 5 milligrams of chlorine for each milligram of nitrite, which means that it's basically borrow that chlorine from the disinfection process. As a result, there is not enough chlorine and there is not enough disinfection, and that's why the plant had problems. So all this together led us to believe that if we have a better control of aeration, especially using, instead of DO, ammonia as a criterion, we can provide much more stable nitrification and at the same time save energy. That's basically it.
Gotcha. So what kind of gave, this is probably both for Alex and for Jim, what kind of gave the implementation team the biggest challenge in implementing this here in Chico?
Do you want to start, Alex?
Yeah, actually, if I may, I would turn that first of all to James, because I think the uniqueness of this project is the fact that this project was driven by operators.
Yeah, let's start with you, James, and then we can move to Jim. You said that you had something you'd like to share as well.
Okay. Would you like me to go first?
Yes.
Yeah, go first.
Okay. Well, I think what really drove us initially, once we kind of, I've been here for about 20 years and I've been in charge. I took over in that transitional time around 2014 when our previous supervisor retired. It really was the fact that we spent so many years not really understanding what was actually going on. We're kind of running a system the traditional way, the way that it was ran before, and you just kind of do it this way, and you just kind of deal with the obstacles that you encounter. And I think with the SRT program coming into effect and it kind of proving some assumptions that we had at the time, it kind of led us down a path of where we really wanted to understand really what was going on out there, since we're so blind to things, a lot of things. So we had some assumptions with ammonia. We had, so this kind of fit when it was proposed. Alex kind of proposed of us kind of jumping into some of this, and we really believed it was going to be in our best interest to try to figure out what exactly was going on. So that led us down to trying to come up with a way to do it in-house, because we didn't really have the funding to do it. So we got, I got a little creative with what we had available to us in the operating budget. We have some talented people, and we have a very talented electrical person, and we started to incorporate components of the project at a time. We started off with a project that diverted. We incorporated previously installed piping that existed at the plant. We're able to tie into that, which allowed us to divert centrate during dewatering times, which allowed us to kind of have our own detention time of that, reincorporating that back into the flow to stabilize ammonia load throughout the day. Now, would you like me to get into more of what drove, or what was kind of what I'm doing now, or the actual details of the project itself?
What were the primary obstacles that you ran into? You said that you had like this talented team, but it was kind of small. What were some of the challenges?
Right.
That were
so
associated with
I would, there more than one aspect of it, but the two primary obstacles would be obviously finding the funding source to do something that would cost substantially more in a large project, and finding the manpower to have time to not only install and to incorporate it, but to also just to be able to use the data, optimize the equipment, understand what's going on, pick the correct equipment. There's a lot that goes into it. Even though we were able to do the project, it absorbed quite a bit of time for the existing staff to do it. So it was definitely a feat to do with what was at our disposal.
Yeah, new
But
thing,
it
always a
comes
learning
down
curve.
to money and manpower, like most things, you know.
Yeah, new thing, always a learning curve.
Yeah,
Yeah, Jim, you
Alex,
said that.
I mean, I'm
Yeah,
sorry. Go
Jim, you
ahead.
Yeah,
said you had something.
yeah. Just a little bit of background that Chico is a microcosm of what utilities are facing across the country. More stringent regulations, stress on resources, whether it's financial from a funding standpoint or just getting operators in to help support the plant. And so this initiative is really a broader based initiative that we agreed to collaborate and sought out Alex to work with us to try to see if advanced automation could solve the problem. And Chico they've kind of has always been a client of ours that's willing to try and to work and to adapt. And so the biggest challenge was really we were implementing a system that we weren't sure how it was going to work. And they came in with a willingness to roll up their sleeves, not just in the implementation phase, but also to work with us as we developed it. We walked into the project with a concept that we could use some pretty sophisticated mechanistic models. And the reality was they didn't work. And so it was Alex's ingenuity and dogged determination to really turn to machine learning that was not our original intent, but was required for it to be implemented. And so I think not just the challenges that James has talked about in terms of the staffing or whatever, we were really, we weren't on the cutting edge, we were on the bleeding edge to make this happen. And so, it was really Alex's hard efforts working collaboratively with staff to implement it, and staff giving us an opportunity to try various options. And to me, that was the biggest obstacle that we had to overcome.
Yeah. So in terms of that machine learning algorithm, I'll toss this over to Alex. Could you talk us through a little bit about kind of like how this works, and what you were thinking about when you were getting this together for them?
Sure, sure. So let me start with the fact that most of the control system in the world today using proportional integral derivative control algorithm that, believe it or not, was developed more than 100 years ago. And still it's a workhorse of any industry, our industry, chemical industry, any industry. And for most part, that fairly simple algorithm works very well. Unfortunately, for activated sludge process, this algorithm doesn't work as well as for other processes for two reasons. First of all, this algorithm was developed when computer didn't exist, so it utilizes a very simple linear equation. Second problem is that it's developed for the processes that do not have much delay. What does mean delay? Delay means that when you, for example, drive and you push the accelerator, you see immediately change in the speed, right? So imagine if you push the accelerator and you see the change in speed in about 2 hours. And what are you going to do during these 2 hours? This is a challenge, right? So those two challenges that activated sludge process has, which is non-linearity and time delay, these PID algorithms are not able to to manage. So there are two approaches dealing with this challenge. All of them, both of them, related to the modeling of the activated sludge process and the aeration process. And these models non-linear, and they can deal with traditionally all consultants are using mechanistic models. What mechanistic models means that it's a model that is based on fundamental equations describing activated sludge system, and when we're talking about aeration, the aeration system. And these models are very well developed and used day in and day out by consulting engineers for design. We try to apply the mechanistic models for activated sludge system part, because the control system for aeration consists mainly of two parts. One part related to controlling the activated sludge with the ammonia control, DO control, and another part controlling just valve position, which is a model of the aeration system, similar to hydraulic systems. So both of these models are very well developed, as I mentioned. However, they are developed not for long-term modeling, not minute per minute or even second per second basis. When it comes to second per second basis, they don't work. We unfortunately didn't find it immediately, and it took us, for example, with a aeration, mechanistic model for activated sludge, it took us years and years and years trying to apply these activated sludge process models to be used for real-time control, and it didn't work. In Chico, we learned, and that was one of the big problems with it. Jim talk about is the fact that this aeration model, which we thought would be much more robust, the mechanistic model of aeration, it didn't work either. So we had to start with practically ground zero for some of those, and we applied machine learning. What is machine learning? Machine learning, unlike mechanistic models, does not have too many assumptions, and it relies only on the historical data. So design engineers, for example, cannot use this approach because there is no historical data when they design new plants. We, however, using data from operation, we can use previous data, and the computer creates the model itself. So instead of us using pre-built mechanistic model, the computer creates a model for each process, and it calibrates it every 30 seconds on its own. So as a result, these models are always properly calibrated. It would be a mistake to say that we just push the button that called machine learning and the system works. There's no such thing as a machine learning algorithm. There's hundreds of thousands of them. Sorry. And to find for each process the algorithm that could be applied of this library of algorithms takes, again, years and years and years. For example, for aeration algorithm, we use so-called random forest algorithm. That basically, it's when computer creates a lot of if-then statements, but instead of we analyzing the data, it's a computer analyze the historical data. It creates like a decision tree with a lot of if-then statements. On the other hand, for DO and ammonia control, it utilizes so-called time series analysis, which is a completely different machine learning algorithm. So machine learning, there are libraries of these algorithms, and to find the algorithm that works for a particular control, it's a challenge. And even if when you find it, to apply it, it takes quite a bit of efforts, because you cannot apply it as is. There need to be, again, some so-called constraints that we have to apply to avoid problems with other parts of the plant. But eventually we made it work.
Yeah. So what, from just in the interest of time, I'm going to kind of combine a couple of the questions that we had left here. The first one was, how did this shift kind of the workload that you were talking about, James and Travis? And then what advice would you have to other utilities that may be looking at something like this? So I'll start with James and Travis on that, and then throw it to Jim and Alex before we close out.
For the workload, I say that we kind of went from a react, like James was saying, a reactive, not knowing what's going on, a lot more maintenance due to and deal that to more of a routine day-to-day operations where we have the confidence that we know what's going on, just taking care of the instruments with the trending and the historical data. We can pinpoint what actually happened instead of just looking at it going, we have all this random data, but we don't know what's going on. And having that confidence of you just being able to not set it and forget it, but to be able to set it and knowing that it's going to be stable and it's not there's no wastewater mystery. It's going to be what it's going to be. So I don't know if James has anything to add to that.
Yeah, from a workload standpoint, that pretty much sums it up. I'd like to touch though that, when it comes to the project itself, there are some aspects that other facilities might run into, but we added, nearly 50 pieces of equipment to an aeration tank that had, nothing but manual control, and we had to do a lot of it where a lot of facilities might have to do the same, where there was no conduit infrastructure to bring a lot of that back, where we ended up doing a lot of this wirelessly, which was a big advantage that we had, someone on staff that was capable of doing that. But as well as it's proven to be very stable and very reliable and can be very cost effective. And a huge driver of a lot of this, is energy savings. We keep talking about process control and, the benefits of that, which from my standpoint, that's the biggest thing, because I want I want the process to be stable. I want it to be predictable. And, that's what drives everything for me. But when it comes to, getting approvals or getting things done, energy is money. And this project has proven out to, save substantial amounts of energy so far, and is looking to do even more as we make, enhancements as we move forward. I don't know if we're going to touch base on really the components, of the project itself, but, those are the two things I really wanted to touch base on.
Cool. Well, I do appreciate you all taking the time today to talk to me, and congratulations again on a top project. It's a huge, massive award, and you guys have done a great job, especially with such a small team.
Thank you.
Okay.